In this video, we'll look at revising charged particles in electric fields. Here we go. First off, we'll go back to the idea of parallel plates, and in between these parallel plates there will be an electric field, and that electric field is constant in magnitude and in direction, so it's the same strength and direction everywhere. Within this electric field, we can accelerate a charged particle with the field or against the field, and in those cases work is being done by the electric field to transfer energy to or from the charged particle. We can calculate how much work or how much energy is being transferred by using this equation here. The amount of work done, the amount of energy transferred, is the charge multiplied by the potential difference between the parallel plates. And this work is being done to either raise or lower the kinetic energy of the particle. So for example, if I had this particle here, which is going to start off with some kinetic energy, and it's moving towards the positive plate. Because it's also positive, the charged particle should slow down because it's going to be forced from left to right in the direction of the field lines, and that means that it's going to slow down, so its kinetic energy will decrease. If it makes it just to the end, the amount of work done to reduce the kinetic energy to zero will again be equal to Q multiplied by delta V. So we can use this information to tell us how much energy the charge has and that it loses if it ends up stopping right at the end when it reaches the positive plate. We can apply it in reverse as well, where if this charged particle instead started over here and started at rest, it would gain kinetic energy from the field and accelerate towards the negative plate. Again, to calculate the kinetic energy that it would gain, we would use the work done by the electric field, because the work done by the field is going to tell us that the energy the charged particle will be gaining or losing. So we're always using this formula here to work out how much energy the particle is going to get, and we'll translate that to the kinetic energy that it will have. This equation here, work equals charge times by potential difference, that's on your formula sheet, and we can rearrange it slightly. We can rearrange it to make potential difference the subject, and it will be work over charge, and that gives us our definition for potential difference. The potential difference is the amount of work done per unit charge to move a charge between the 2 points. More literally, potential difference, it's the work done per unit charge to move a positive charge between 2 points. And in the electric fields topic, we often talk in terms of the positive charge and what the positive charge is doing. So potential difference is the work done per unit charge to move a charge between the 2 points where the potential difference is between. There we go. Now, this equation is also useful in telling us what an electron volt is. If we have the potential difference as just 1 volt and the charge being that of an electron, 1.6 by 10 to the power of minus 19 coulombs, forgetting my C for coulombs there, which is the charge of an electron, we can calculate how much energy that would be. So the work done there would be the potential difference, which is 1, multiply the charge, which is 1.6 by 10 to the power of minus 19, and we get 1.6 by 10 to the power of minus 19 joules, like that. Now this amount of energy here is exactly 1 electron volt, so it's got an alternative unit of 1 electron volt, 1 eV, like that. It's just another unit of energy that's used for much smaller things, and we define it using 1 volt and the electron. So the electron volt, it is a unit of energy. It's the work done to move an electron through a potential difference of 1 volt. think about electron volt, one electron moving through 1 volt. It's the amount of energy needed to do that, to move an electron from here to there, or there to here. It's moving through a potential difference of just 1 volt, and that's what an electron volt is. If we want to convert between electron volts and joules, we use the charge of electron, 1.6 by 10 to the power minus 19. So we multiply by that value if we're going to joules, and we divide that by that value if we're going to electron volts. Back to our parallel plates and the electric field inside. Now, the electric field between parallel plates is the same size and direction as demonstrated by the electric field lines. We need to remember that. So the electric field there, it is the same size and direction everywhere. And we call that a uniform field, or uniform electric field here. In the same sense that on the surface of the planets we have a pretty much uniform gravitational field, and that's why we get the same acceleration everywhere of 9.8 meters per second. So here, if we place a particle here, it should get the same acceleration everywhere. Now, the magnitude of the electric field between these plates is given by an equation. So we use E is equal to the potential difference divided by D. So we just need to know what the potential difference is, and we also need to know the distance between the plates. So this distance here, all the way across, D, we'll need to know that to calculate what the electric field strength is. And the fact that we can calculate the electric field strength by using the potential difference and dividing it by D gives us an alternate unit for it, because potential difference is measured in volts and D, the distance, is measured in meters. You can see electric field strength being measured in volts per meter like that, or V M power of -1 there, like that. So if we place a charged particle in this field, it will accelerate in the direction of the field lines, or if it's a negative charge, in the opposite direction of the field lines. And the magnitude of the acceleration is given by an equation. You get the acceleration by doing the charge multiplied by the electric field strength divided by the mass, like that. Now, because the acceleration is directly proportional to the electric field strength, it means that the acceleration is also the same size and the same direction all the time for the particle that's in there, because it's proportional to the electric field strength. So the acceleration is also uniform, same size, same direction. So, as acceleration is equal to QE over m, the acceleration is also going to be uniform with a constant size and constant direction. So, we need to derive the acceleration formula there. To do that, we'll start off with Newton's second law. So we would explain that Newton's second law states that acceleration is equal to the net force over the mass. Okay, so that's into Newton's second law, like that. And we need to think about where this force is coming from. We have a charged particle in an electric field. So the electric field is the source of the force, and the electric field strength is given by F over Q, like that. And that's because we've got a charged particle in an electric field. It's lagging here. That's the equation because we have the electric field strength given by F on Q, and that means the force on the particle should be given by EQ. And you've probably guessed already that if we call this equation 2 and the guy up here equation number 1, then all we'll be doing is putting F equals EQ into this F here. So we're going 2 into 1, and that's giving us that the acceleration is going to be equal to EQ or QE, doesn't matter which way around you do it, over M, like that. If we backtrack a bit here, just a reminder, we have an electric field here that is uniform. It's the same size and direction everywhere between the parallel plates. Because it's an electric field, charged particles will accelerate in that field, and the acceleration is given by this equation here. So because acceleration is directly proportional to the electric field strength, the acceleration will also be uniform with constant size and direction. So we can have movement of charged particles in here, and they'll only get acceleration of a constant size and direction. And that's going to describe the kind of motion we expect to see for particles that are in this field. Describe the motion. Note that a particle's velocity when it enters this field can be broken up into a perpendicular component and a parallel component. I'll illustrate. Here is our particle with a velocity within the field. We can break this up into two components. We've got a component of the velocity that is perpendicular to the field. Oh, pardon me. 1 second. Okay, here we go. So there's our velocity there. That is going to be perpendicular to the field. Because that velocity component is at an angle that is a right angle to the field lines in red. And then there will be a component of the velocity that is parallel to the direction of the field, which is this little component here. Okay, and together they add up to the total velocity of the particle at that instant in time. And the electric field will only have influence on the parallel component. It will only accelerate that parallel component and increase it or decrease it. Whereas the perpendicular component will always stay constant because that right-angled electric field and acceleration won't affect it, in the same sense as projectile motion, where the gravitational field of the planet goes downwards, so therefore the vertical velocity, which acts upwards and downwards, that component gets affected, whereas the horizontal component of the velocity on Earth is not affected at all, and that will stay constant. So it's the velocity that's perpendicular to the field that will remain constant, whereas the velocity parallel to the field, that's going to be the one that's affected by the acceleration. And this results in parabolic motion, motion similar to projectile motion that we experience and see on Earth and in the projectile motion topic. So parabolic motion is what we get for charged particles within an electric field for these reasons. The electric field is uniform. Acceleration is given by this equation, so it's proportional to the electric field strength. That means the acceleration is also uniform in size and direction. Only the velocity that's parallel to that acceleration will be changed by that, whereas the perpendicular component will be constant, and that will give us parabolic motion where one component of the velocity is changing and the other component remains constant.